Welcome to Plutus IAS. And today we are covering the effect of hydrogen bonding on the IR spectra. As you guys are already well aware that IR spectra talks about the vibrational levels and how the different atoms vibrate. There can be your stretching vibrations, whether asymmetric, symmetric, then your bending vibration, again whether in plane or out of plane. Based on that, the vibrational energy levels change their energy and there will be a shift in the spectrum. Now, this shift can be utilized for explaining different behaviors, figuring out patterns. For example, a shift in case of intra and intramolecular hydrogen bonding can be differentiated based on the extent of it. For example, in terms of strength, your intermolecular hydrogen bonding is stronger compared to intramolecular. So that means there will be a difference in types of the spectra or the bands that you will get for inter and in case of intramolecular hydrogen bonding, which can be utilized to differentiate between different types of molecules. And today we're going to explore those possibilities and how those shift arises. So for the first part, we need to be very cautious and need to explain how this entire shift occurs. So first thing, the entire IR spectrum is based on Hooke's law. Based on Hooke's law that states that wave number of a species is given by 1 by 2 pi c under root k by mu, where k is referred to as your bond constant, and it is a direct measure of bond strength. So that means stronger bond will have a higher wave number and will appear higher at the very start of the spectrum. Now, before you go for that, you also need to remember that polar bonds also also appear at higher wave number, at higher wave number. This arises because for a molecule to be IR active, it should have dipole moment it should not have a dipole moment equals to 0. In polar bonds, the mu is given by charge separation by the distance that in between them. In case of polar bond, the charge separation and the distance decides the bond movement, which helps in explaining that why polar bonds appear at higher wave number. So, for the case of molecules, in case of taking examples or shift in bands in IR, shift in bands of IR can be divided into two categories because of hydrogen bonding. First, the shift that you can see is in case of free OH group. A OH group which is neither involved in intermolecular hydrogen bonding or your intramolecular hydrogen bonding. Then you have molecules which are involved in hydrogen bonding. The molecules which are involved in hydrogen bonding can further be separated on two types. One being as hydrogen bonded intramolecularly and the one being hydrogen bonded intermolecularly. For the first case, in case of free OH group, for the example I am taking methyl alcohol CH3OH. For methyl alcohol in very dilute solution, the solvent that I am using here is CCl4 to avoid any interaction between the alcohol molecules. In free OH group, we get a very sharp and distinctive peak at wave number about 3660 centimeter inverse. Why? Because this methyl alcohol is surrounded on all sides by CCl4 solvent, which prevents their interaction from nearby alcohol molecules, thereby suppressing the intermolecular hydrogen bonding between them. And that's why there is only one single peak, there is no average exchange of the bonds. That means OH like this. It will remain like this because if you are considering hydrogen bonding, let's say if you are talking of intermolecular hydrogen bonding. In intermolecular hydrogen bonding, because there is a shift in electron density by interaction between the adjacent alcohol molecules, the bond polarity increases, and because of which this bond gets elongated, but the charge separation do not increase with the exact same strength. So if you go for a concentrated solution, you will get one sharp peak corresponding to free OH group. But in concentrated solution, since the alcohol molecules can interact with one another, which will lead to increase in the bond length because of bond polarity, and because of which the bond constant decreases. When the bond constant decreases for it, that means there will be a decrease in the wave number as well, which will appear at like this. This corresponds to intermolecular hydrogen bonding, and this peak appears at about 3510 centimeter inverse for the case of methyl alcohol. Notice there is a large difference between these two peaks. This peak is sharp but narrow. This peak is broad in nature. Why it is broad? Always remember, whenever hydrogen bonding occurs, we always get broad bands or peaks in our IR spectra. Why is it so? For the case, like I've stated, when you are going for inter or whether intramolecular hydrogen bonding, you will always find because of interaction between them, these molecules may come close to one another, and at the same time there can be proton exchange between these bonds as well. And because of proton exchange, there is a continuous bond formation and bond breaking. So that means here the bond length will increase, and then when formed it will decrease. So there is a continuous change in case of vibrational frequency. And when there is a very fast change in vibrational frequency, your IR spectra cannot detect it, or your spectrophotometer cannot detect it. So instead of giving you a sharp peak, it takes average of those vibration and it gives you a broad peak in a average way to explain that there is extra phenomena that is occurring in case of a intermolecular hydrogen bonding. Now another one, if you go for intermolecular hydrogen intramolecular hydrogen bonding, it is weaker than intermolecular hydrogen bonding. If this is weaker than intermolecular hydrogen bonding, that means the decrease in K value is lesser. So the wave number will also be the decrease in wave number is also be lesser. So when it comes to IR spectra in case of intramolecular hydrogen bonding, again because of average length, it will be broadband and then it will be for IR. This band refers to your intramolecular hydrogen bonding. This refers to inter. this refers to sorry this refers to free OH group, and this refers to inter. It appears at a wave number of about 3610 centimeter inverse. This is at 3510 centimeter inverse, and this is at around 360 centimeter inverse. So just by looking at the graph and based on the positions of the peak, you can predict whether the molecule is undergoing is present as a free hydroxyl group, or whether it is taking part into inter or intramolecular hydrogen bonding. Now, factor that can affect different kinds of shift or the bands. First thing, intermolecular hydrogen bonding, if you see, hydrogen bonding is temperature and concentration dependent. Concentration dependent. While intra is independent of all those things. Is independent of temperature and concentration. So that means if I'm taking a molecule which is, let's say, ethylene glycol, CH2OH, CH2OH, which can take part in intermolecular hydrogen bonding and intra. So here it is taking part into intermolecular hydrogen bonding. Here it is taking part into intramolecular hydrogen bonding. Now, making the cases for dilute solutions, again, then for less concentrated or your neat solution. Neat means neat solution. Neat means you are taking 1:1 ratio of ethylene glycol plus CCl4. In this case, you are taking 1:10 concentration, and for this you are taking 1/100. In case of very dilute solution, the distance between the ethylene molecules are very large, separated by CCl4 molecules, so they do not interact with one another. But still they can have intramolecular hydrogen bonding, and since they cannot interact with any other group, they can also freely exist as the hydroxyl group, so there will be a sharp peak in them. In case of less concentrated solution, now the number of ethylene glycol molecules within the solution increase, and because of that increase, what happens is, now intermolecular hydrogen bonding will come into play, and you will start witnessing its peak as well. Finally, if you go for neat solution, you will find neat solution, now every single ethylene molecule will interact with one another, so a chance of existence of a free OH group is very less. So in neat solution, the free hydrogen peak will get completely vanish, and only intermolecular hydrogen bonding exists. Since intramolecular hydrogen bonding in case of ethylene glycol can never be eliminated, so we are left with that intermolecular hydrogen bonding is dependent on concentration. Hence, if you are changing the concentration, you can figure out whether the molecule is taking part in intermolecular hydrogen bonding or not, simply by looking at the spectra and by knowing the concentration of it. Next, proving the existence of temperature. In case of temperature, what we'll find is, in case of temperature, increasing the temperature raises the kinetic energy of the molecule. Kinetic energy of the molecule means every alcohol molecule will try to move away from one another. And since hydrogen bonding is a distance dependent phenomena, the extent of hydrogen bonding decrease with the distance. With distance, if you increase the distance, that means intermolecular hydrogen bonding will vanish, and finally your solution at elevated temperature behave like diluted solutions. So I hope this would have cleared all your doubts regarding how the shift in IR spectra occurs, how different bands can tell us different phenomena that exist in a molecule and how they affect the position of those bands. In case of any doubt, you can add it to the comment section, or if you have any other queries, or if you want a specific topic on which the video needs to be made, please also add it to the comment section and we'll get back to you. That's all for today. Thank you for joining us.